In this lesson, we're going to be solving this problem. This problem is under the strength of material. It deals with a compound. Read as follows. Two pipes, one of a copper and the other of a steel, are rigidly fixed together at their ends. The steel pipe fits neatly inside the copper pipe. The cross-sectional area of a copper pipe is 0.0056 meters squared, and the area of the steel pipe is 0.0044 meters squared. Calculate the stress in each material when the temperature is increased by 25 degrees Celsius, and we're given the Young modulus of a steel pipe is 200 gigapascal and the Young modulus of the copper it's 100 gigapascal. Then we're given this, the coefficient of the steel and also the coefficient of the copper. Our goal is to calculate the stress of each of these material, to calculate the stress of the copper, to calculate the stress of the steel. Since we know that the formula to calculate the stress, it is this equal to the force divided by the area. That is the formula to calculate the stress. We'll be introducing the formula to calculate the force when the compound bar are parallel. So the formula that we're gonna introduce here to calculate this force, that force we will use it when we calculate the stress for a copper property, and we will use it to calculate the stress of a steel pipe. We'll use the same force that we'll calculate now using that formula that we'll introduce. So it is F is equal to, then you open the bracket, it is 1 divide, then the area of a steel pipe times the Young modulus of a steel pipe, then plus 1 divide by the area of a copper times Young modulus of a copper, close bracket, it's equal to a change in temperature, open bracket, then the coefficient of the copper minus the coefficient of the steel, close bracket. That's the formula, but this formula you use it when these compound bars are in parallel, not when these compound bars are joined at the end, which when they are in series. We don't use this when they are in series, but here are on parallel. They are fixed together at their ends. That means they are parallel. So to find the force, we use this formula. Then let us calculate the force here. Before we calculate the force, let us extract the data that we have. Here we have the area for steel. It is 0.0044 meters squared. Then we have the area for the copper. It is 0.0056 meters squared. Then we have the change in temperature. It is 25 degrees Celsius. Then we have this Young modulus for steel, Young modulus for copper, and also the coefficients here. Then let us substitute. It is F that we are looking for, then open the bracket, 1 all over, then the area for steel, it is 0.0044 times the Young modulus for a steel, it is 200 times 10 to exponent 9 to exponent 9. That is a gigapascal plus N1 divided by the area for a copper. It is 0.0056 times the Young modulus for a copper. It is 100 times 10 to exponent 9. Then close bracket. It's equal to the change in temperature. Here it is 25 degrees. Then here the coefficients for the copper. It is 18 times 10 to exponent -6 minus 12 for the steel. It is 12 times 10 to exponent -6. It is like this. Our goal is to find this force. Then when you break down this, it 2.92 times 10 to exponent 9. Then this side 1.5 times 10 to exponent 4. Then from here the force, it is 51369.86 newtons. That's the force we're gonna use in calculating both stress for a copper and stress for the steel. So let us calculate it. Here the formula to calculate the stress for a steel. Say this force divided by the area for a steel. Substitute here the force. This one, it is 51369.86 divided by the area of a steel. It is here 0.0044. The answer here, the answer to be 9173,189.29 Pascal. Point here. Then this, it's gonna give you 9.2 megapascal. It is like this. This is a stress for steel property. Now we calculate the stress for the copper. It is stress for a copper, this force area for a copper. Then we substitute here, same force, 51369.86, then divide by the area for a copper, this one 0.0056. Then this, the answer is 116,74968.18 Pascal. This it's gonna give 11.7 megapascal. That's the stress for a copper. That's the stress for a steel that we require to find. We require to find the stress for a copper, the stress for a steel. That means we have reached our final answer.